Okay, good. Then let's start with this fixed tutorial, right? Okay, so question number one, the following output is given, right? We need to determine their frequency response provided if the system is LTI, right? That means if the system is linear time invariant. So for A, x of n is equal to 1, half to the power of n, right? That is the input that gives a output of y of n is equal to 1 upon 8 to the power of n, right? So if you see this particular function, x of n and y of n, both are not bounded, right? Both of them are not bounded. So what happens is that since both of them are not bounded, they are not summable, right? From negative infinity to infinity, they are not summable, because if you try to add them up or you try to sum them up, they will give you a infinite value, right? Because it will keep growing, right, towards the negative half of the negative half of the axis, right? So due to not being summable, right, there is no Fourier transform that exists for both x of n and y of n, right? And the other thing is that if you see closely, you can relate y of n with x of n as x to the power of 3, right? In that particular case, x to the power of 3 is non-linear. So if the system is non-linear, we do not have to determine the frequency response for the particular system, right? Like in this particular case. Then part B, again, we are given the same sequence, but this time the sequence is bounded by u of n, right? Basically, your system will start from 0 and go towards the positive infinity, right? So in this particular case, both the graphs will be something of this kind, isn't it? Right? So it will be coming towards 0 as it approaches infinity. So since it is bounded, right? So what happens is that there is a Fourier transform that exists for this particular form. So we can directly apply the Fourier transform properties in this particular case. That would be the property is a to the power of n u of n is equal to 1 upon 1 minus a e to the power of minus j omega, right? So you can just look up for the Fourier table and use that particular property in this particular case, right? So please look up for the table of discrete Fourier, DTFT, right? Discrete time Fourier transform, right? The table for that. I believe all of you are familiar with that, right? So using those properties, we can transform x of omega and y of omega, right? The same case. Then what we can do is we can find our h omega, isn't it? H of omega can be found by y of omega upon x of omega, right? So basically dividing these two, right? So if we perform that, we'll be ending up with 1 minus 1 half e to the power of minus j omega upon 1 minus 1/8 e to the power of minus j omega, right? So basically we have found our frequency response in this particular case, right? Since both are summable, so we have determined the frequency response in this particular case. Moving on to question number C, x of n is equal to e to the power of j pi upon 5, right? Y of n is equal to 3e positive j pi upon 5, right? So in this particular case, you can see that if you find h of n, that would be y of n upon x of n, you can see that it is just 3. And if you try to determine the frequency response of this, you'll just be getting 3. So h of omega is equal to 3 for all omega. Okay, same goes for d. Again, in this particular case, you can see x of n is equal to e to the power of j pi upon 5 u of n. That gives you y of n is equal to 3 e to the power of pi upon 5 u of n. Again, these two are bounded, right? What happens is in this particular case, what happens is, again, the same situation exists as above, but this time it is h of omega is equal to 3 for all omega, but more particularly for pi upon 5, right? So h of pi upon 5 is equal to omega. E x of n is equal to x n plus n1. That gives you y of n is equal to y of n plus n square, n2, right? In this particular case, n1 is not equal to n2. So like we know that for a system to be time invariant, a delay in the input should result into a similar delay in your output, right? But in this particular case, since n1 is not equal to n2, the system is not time invariant. So since that is the case, we do not need to identify the frequency response for this particular system, right? Question number 5.3. Consider an LTI system with impulse response h of n is equal to half n u of n, right? We need to determine the magnitude and the phase response for this particular form. So okay. So in order to determine h of omega, what we do is we can again use the Fourier transform property rather than evaluating the whole thing. In this particular case, we know that the Fourier transform exists for half to the power of n u of n, right? So that will be in this particular form. We have already found that in this particular case, right? 5.1b. So we can use the same property over here as well. So once we have that, we can further simplify this, and we can write e to the power of minus j omega as as cos omega minus j sine omega, and half is expanded into it, right? So half is multiplied with cos omega minus half j sine omega, right? So we have this. So in order to determine the magnitude response, what do we have to do? We can rewrite both the numerator and denominator in form of polar form, isn't it? We can write it in polar form. So that would be to find the magnitude response, we just need to find the magnitude of this numerator and the magnitude of denominator. So magnitude of numerator divided by magnitude of denominator. So in this particular case, the magnitude of 1 would be 1 just itself, divided by the magnitude of this bottom part. You can see there is a real part and the imaginary part. This is the real part, while this is your imaginary part, right? So to find the modulus of that, that is real value squared plus imaginary value squared root of that, right? Isn't it? So this is what we have done over here in this particular case. And then basically using all the trigonometry rules that we have learned throughout. Okay. Okay. Basically using the trigonometry rules, we can evaluate this part, right? It is what has been done over here, and then we get this particular value, right? What I want you guys to do is to actually practice this on your own, right? Try to evaluate this and find how we actually got this, right? But it is pretty simple. You have just basically squared this, evaluated this, right? Expanded this, and then simplified using the sine squared plus cos squared theta rule. That is going to give you 1, right? This one is just going to give you 1 in this particular case. So based on this, this will be our magnitude response. However, the phase response is not given. So what we need to do is to find the phase of this and phase of this divided by phase of this. So in this particular case, we can assume the phase of this as A, right? So that would be phase of 1, that is phase of a real value, and it is positive. So the angle will be 0, isn't it? So 0 minus the angle of this bottom part, that will be going to give me angle of A, which is equal to negative angle of A. So the phase response is basically negative angle of this bottom part, right? So in order to determine A, it is basically in order to find, where is it? So that would be tan inverse in order to find the angle of this, right? A, that is tan inverse of, so this is not working. Okay. Tan inverse of imaginary value holding upon real value, right? So in this particular case, the imaginary value is half sine omega, right? This is your imaginary value. Holding upon, sorry, it will be negative half sine omega, right? Will be your imaginary value, and your real value will be 1 minus half cos omega. This is your real value, and this is your imaginary value. I hope everyone gets this, right? This is basic simple mathematics that we have learned in our Form 7 maths, right? So that's how we evaluate this, and that will be our phase response. So basically, whatever angle we get over here, that is tan inverse of half sine omega holding upon 1 minus half cos omega, right? And the negative value of that, right? So that's how you get the phase response for this particular term, right? I'll also be, okay, never mind. I want you guys to do this, evaluate this, and when we'll be running the tutorial session, the remedial sessions, every now and then, I want you guys to come up with your difficulties, whatever you have faced, right? Try it out, try these problems on your own, and let me know, right? Now, moving on to question number 5.4, right? Just before moving on to question number 5.4, I'd like to just tell you that this session will run for 40 minutes, right? Just in case if this session disconnects after 40 minutes, I want you guys to use the same link and connect back, right? It will take about 1 or 2 minutes. You can reconnect to this particular session again, right? Because I'm not sure if we are going to be able to complete this session in 40 minutes or not, right? I hope everyone gets that, right? And I want everyone to rejoin, just in case if the session disconnects before I finish. I want everyone to rejoin because I'll be taking the attendance at the end of this session, right? Okay, question number 5.4, determine and sketch the magnitude and phase response of the following systems. Just in case if you haven't followed up till here, if you weren't able to understand how we got the phase response, this is where we'll be again explaining the phase response part, right? So you can use the same concept that we'll learn in 5.4 in 5.3 as well, right? In this particular question, because the solution hasn't been given, right? But I want you guys to try it on your own and let me know if you find any difficulties. However, I've explained the theory behind it, right? Okay, determine and sketch the magnitude and phase response for this particular term, right? Y of n is equal to half into x of n plus x of n minus 1, right? If you find the Fourier transform of this, that will be y of omega is equal to half. Half is a constant, so we leave it like that. And then x of n is x omega, right? X of n converted into frequency domain will be x omega plus x omega multiplied by the delay that would be written by e to the power of minus j omega, right? So what they have done in this part is that they have factored x omega out, right? All right. So that's how we get this particular part, right? So we need to basically determine the magnitude and the phase response for the system. In order to determine that, we need to find the system behavior or the system response or system frequency response, right? That is basically h omega. So h omega is y omega upon x omega. So what we can do is take this x omega and divide it on the other side. We'll get our h omega, right? So if we do that, we'll be ending up with just this particular part. We'll be just left with this particular part, and that is what is happened over here, right? Now, in order to determine the magnitude response, okay, we are left with this. Sorry, we are left with this. We can further simplify this, right? We can factor e to the power of minus j omega upon 2. We can factor it out, and we can see that e to the power of j omega upon 2 plus e to the power of minus j omega upon 2 divided by 2 would represent cos omega, isn't it? Cos omega upon 2. So we can rewrite this as cos omega upon 2, right? This is what we get. We can simplify this and this, right? As cos omega upon 2, right? So that can be written as cos omega upon 2 multiplied by e to the power of minus j omega 2, right? This is the simplified version of this particular term, right? Now, to determine the magnitude response, we basically need to find the magnitude of this term. Clear this, right? Yeah, we need to find the magnitude of this multiplied by the magnitude of this. Remember, when we are using the polar form of a complex number, it is best to use polar when we are multiplying or dividing, right? And it is always best to use what form is that? The Cartesian representation, I believe, right? The normal representation where you get a real plus real value plus imaginary value. That Cartesian representation can be used when you are adding or subtracting. So in this particular case, you can see both the terms are being multiplied. So it is always best to use the polar form, right? So to find the magnitude response, we find the magnitude of the first term and magnitude of the second term, multiply both for the magnitude. So in this particular case, you can see cos omega upon 2 is a real number, isn't it? So the magnitude of this will be the magnitude itself. This will be the magnitude itself. While the magnitude of e to the power of minus j omega 2 is just 1, right? Isn't it? The magnitude 1 is not written. However, the magnitude would be 1, right? So it is already given in polar form. So basically that would be 1 multiplied by magnitude of cos omega upon 2, right? So we'll be just left with magnitude of this, right? So we just need to plot this. So plotting cos omega upon 2 will result into something like this. So when your cos 90 or cos pi upon 2 will give me 0, isn't it? So in this particular case, when when omega is equal to pi, we're going to get 0. When omega is equal to negative pi, we are going to get 0. When omega is equal to 0, the whole term turns into cos of 0, that is going to give me 1. So basically you get a half circle if you try to draw for the frequency range, between the range negative pi to pi, right? While for the phase response, again, in this particular case, we just need to find the phase of this, right? Phase of this, sorry, clear this. Phase of this, that is angle of this term here, multiplied by the angle of this term here, right? So we know that the angle of a real value is 0. So in this particular case, it will be just 0 degrees. So when we are multiplying, we add the angles, right? So the angle of this particular term will be just negative omega upon 2, isn't it? So angle of this is 0. So angle of this particular term is negative omega upon 2. So basically the phase response will be 0 plus negative omega upon 2. So the phase response of this particular term is equal to omega upon 2, right? Sorry, negative omega upon 2. Or the other way you could have just read this as this is the magnitude part, and this part is the Euler's formula, right? So this, just removing the omega, this part represents my angle, right? That's the other way of reading this, right? So in this particular case, the phase response is negative omega upon 2. So plotting that, you'll be getting something like this, right? That is negative omega upon 2. That would be, if omega is equal to pi, so that would be negative pi divided by 2, right? Negative pi upon 2 will going to give me a rough value of 1.57. So at pi, we are getting roughly 1.57, right? So in this particular case, just don't get confused. This is just the numerical representation of this, whatever we get over here, right? If you have any questions, just do type it in the Dropbox, or just using the reaction, you can raise your hand, right? Just in case if you don't understand anything. Okay. Question part B of this, again the same procedure. We are given an equation y of n is equal to half into x of n minus x of n minus 1, right? Again, evaluating this, we'll be ending up with y of omega is equal to half into 1 minus e to the power of minus j omega. x of omega, right? It is the same thing, but this one has been just simplified, right? Slightly simplified. X omega has been factored out. Then what we need to do, since we need to find the magnitude and frequency response of the system response, we need to find the system behavior, I mean h of n, right, or h omega. So what we can do, we can find our h omega. So take this x omega and divide it on the other side. That will be our h omega. So basically we are left with this particular term, right? So that is what we are getting over here, right? And then we can further simplify this by you can see we can just simplify this by factoring e to the power of minus j omega 2. So we'll be left with for this particular term, right? I'm simplifying this. So we are left with half. If it's factor out e to the power of minus j omega 2. So we are left with, excuse me, I'm having a little bit difficulty writing on this screen, right? So that will be half into e to the power of minus j omega upon 2 into e to the power of j omega upon 2 minus e to the power of minus j omega upon 2, right? Isn't it? We can rewrite this term. We can rewrite it as this, right? Then from this, we can see if we need to write it in terms of sign, we can multiply top and bottom with j, right? So basically, we can multiply this part. We can multiply the whole term with j upon j, right? If we multiply both top and bottom with j, we'll be left with, let me clear this. So we'll be left with it will be j e to the power of minus j omega upon 2 sine of omega upon 2, right? Right, that's how we write it, right? And then this is what you can see over here, right, with this particular term. And then we can write this j in form of polar form, isn't it? So j will be having a magnitude of 1, and the angle of this j will be 90 degrees, right? Or just pi upon 2. So this represents j, right? So once we have this particular term, again, we just need to find the magnitude and the phase response. Again, you can see this whole term is written in the form of r e to the power of j theta. So this becomes my r, right? Sine omega 2, right? This is my r, while my theta is minus j omega upon 2 plus pi upon 2. All right. So plotting this sine omega upon 2 will result into something like this. So the diagram drawn over here is between 0 till pi, right? You can draw it up till from negative pi till pi, or from 0 till 2 pi. That is fine, as long as you should be getting something like this for the range of 0 to pi, right? This is the shape that you'll be getting, right? And then the angle part is represented by, you can further simplify this. The theta can be written by the theta part can be represented by pi upon 2 minus omega upon 2. Okay, so this is basically my phase response. So at pi is equal, when omega is equal to pi, so it will become pi upon 2 minus pi upon 2. So that is what we are getting, that is 0. And when omega is equal to 0, right, when omega is equal to 0, this term turns into 0. So we are just left with pi upon 2. So this is the pi upon 2 value, right? And this is something, this is the shape that we are going to get if we plot this particular part, right? Please mute your mics if you don't have anything to speak about, right? If you need to speak, please write in the chat box. So moving on to the next question, right? Again, the same thing has been done over here as well, right? The same part, again, rewrite it in terms of omega and then simplify it, right? They have written it in terms of this. And then we find our frequency response, the system response, that is h omega, that is in terms of this, right? This is what we get. Again, we can rewrite it in terms of sign because we have a minus over here, right? In this particular case, we can write it in terms of sign, and this is whole thing upon 2. So we can multiply the whole equation by j upon j, right? If we multiply the whole equation by j upon j, we'll be left with e to the power of omega minus e to the power of j omega, whole thing upon 2j multiplied by j outside. So this particular term here represents j. Remember over here on the previous equation, j is equal to e to the power of j pi upon 2. That is the same concept applied over here, right? While this whole term can be further can be rewritten as sine omega, right? So we get something like this. Again, it is in the form of r e to the power of theta. So basically, we can take out our magnitude, that is sine omega. So we just need to draw that particular part, sine omega. So if you draw it between 0 till pi or 0 till 180 degrees, so you'll be getting a resulting shape of this for the magnitude response, right? While the phase response is constant at pi upon 2, regardless whatever the omega value is, right? Isn't it? The phase is not dependent on omega, so it is a straight line, right? Pi upon 2. Likewise, it goes for these two parts as well, right? In this particular case, for D, the frequency, the system response comes to cos omega, right? The system response is cos omega. So basically, we do not have an imaginary part. We just have a real part, right? So this is basically my magnitude. That is magnitude of cos omega. So if you draw this, we'll be getting a shape of something like this from 0 between the range of 0 till pi for omega, right? So we should be getting a range of something like this. So we know that from 0 till 90 degrees or 0 till pi, we get something like this. And we know that the magnitude is the absolute value, isn't it? The absolute value of the real part. So the part that goes down is reflected at the top, right? So this is what you get for the magnitude response. While for the phase response, right, this half represents this particular half represents the guys, your mics are on. Okay, anyways. Okay, just a quick recap. If we need to draw this cos omega, we are going to get the cos graph of something like, oh, sorry. Yeah. If we need to draw that, we are going to get a cos graph of something like this, right? So up till here, it is up till pi, and up till this particular point, we are getting 2 pi, right? So this is the particular part that is being represented over here. So magnitude is basically the positive, the magnitude, regardless of whether it's negative value or positive value, isn't it? So the magnitude of from here till here is the positive part, right? This particular part is directly reflected here, while the negative amplitude is reflected as positive over here, right? This is the part. Okay, just in case if you don't understand, you can try plotting this, right? While the angle part from here till here, it's the positive part, right? Isn't it? When the angle is positive. So if it's a real value, if it's positive value, the angle is 0 degrees, isn't it? So that is the part over here. We don't have an imaginary angle, so the value will be 0. When we move from this particular point till this particular point, the value starts to change. This cos omega value starts to change or result into a negative part, right? A negative result. So if you have a negative real value results into real amplitude and e to the power of j pi, isn't it? Right? The angle is 180 degrees, right? Isn't it? So this is what is being plotted over here, right? So you can try out the other parts of this particular problem, right, during your spare time, and we can revise it during our remedial, right? We can practice this particular part. Question number 5.9, we need to determine the frequency content of the outputs of the following systems to the input signal, right? So x of n is given, so we need to find the frequency component of the other parts of this question, right? So part A is y of n is equal to x of 2n. So basically what do we have to do in place of n in this particular question? We need to substitute it with 2n. So substituting this will result me with a cos pi upon 4 multiplied by 2n, that will simplify as this particular term over here. So based on this, our omega value is pi upon 2, right? So the frequency component of this particular equation is pi upon 2. For B, y of n is equal to x squared of n. So basically we need to take x of n squared. We get something like this, and we can further simplify cos squared pi upon 4n using the double angle formula, right? So cos squared a is equal to cos of 2a plus 1 upon 2. You can check the property. Based on that property, this cos squared pi upon 4 upon n, multiplied by n, is expanded, right? Is evaluated, right? And based on that, we get a simplified version as this, right? This particular term, that is half a squared plus half a squared cos of pi upon 2n, right? So from the first term, that is half a squared, we know that our omega is equal to 0. From the second term, that is half a squared cos pi upon 2n, the frequency component is from the cosine function, that is pi upon 2, right? So that is pi upon 2. So the frequency components are omega is equal to 0 and omega is equal to pi upon 2. C, y of n is equal to cos pi n multiplied by x of n. So basically, again, we just need to multiply x of n with cos of pi upon n, right? And then using the trigonometric properties, we can further simplify this and we can rewrite it as this particular term, right? So we get two particular terms, right? So based on this, the first term, this particular term has a omega value of 5 pi upon 4, right? And this particular term has a omega value of 3 pi upon 4. So the frequency components are 5 pi upon 4 and 3 pi upon 4, right? Question number 5.11, determine the magnitude and the phase response of the multi-channel y of n is equal to x of n plus x of n minus m. At what frequency does h omega is equal to 0, right? So first thing, we need to determine our h omega, right? So we need to rewrite this in terms of frequency. So transforming y of n into frequency domain will give me y omega, which is equal to x omega plus x omega multiplied by e to the power of minus j omega m. So we can factor out x omega, right? If we factor x omega out, we'll be getting something like this. Then we can take this x omega and divide this side, right? Y omega divided by x omega will give me h omega. So basically I'm left with h of omega, which is equal to 1 plus e to the power of minus j m, right? Then we need to, it says we need to find the magnitude and the phase response of the multipart channel at what frequency, so we basically focusing on the second part, at what frequency does h omega is equal to 0. So basically taking this particular part, the magnitude will be represented by, magnitude of this will be, we can further expand this, right? Sorry, we can expand this, rewrite h omega as 1 plus cos of omega m, and then that would be minus j sine omega m, right? So this part h omega can be written as 1 plus cos omega m minus j sine omega m, right? We are expanding this particular term that is represented by this particular term, right? That is cos omega m minus j sine omega m. Then what we need to do is, in order to find the magnitude response, again, magnitude response can be given by basically evaluating this particular part. This particular part is written in the Cartesian form of complex numbers. So that is, magnitude can be given by, magnitude R can be given by root of real squared, right? Plus imaginary squared, isn't it? So magnitude will be given by that, while our phase can be given by, as earlier explained, tangent inverse of imaginary part. So in this particular case, the imaginary part is negative sine omega m divided by 1 plus cos omega m. That is the real part, right? So tan inverse of imaginary value upon real value, right? So that will give you the magnitude and the phase response. Now we need to determine at what frequency does h omega is equal to 0. So at what frequency h of omega is equal to 0. So we can see from this particular case, our magnitude will be equal to 0, isn't it? Right? In order to determine the frequency, we can just set h omega, the magnitude of h omega equal to 0, isn't it? So if we do that, we get the magnitude response as 2 cos omega m upon 2, right? The magnitude of that is equal to 0, right? So this is the magnitude response using the normal magnitude magnitude properties, right? I mean, the normal form of evaluating the magnitude part, we end up with 2 cos omega m upon 2. So based on this, we know that our magnitude is equal to 0. So basically, we need to set this equal to 0. So this term will only be 0 if cos of omega m upon 2 is equal to 0. And cos function is equal to 0 only at pi upon 2, isn't it? Or 2k plus 1 upon pi upon 2, right? So in that particular case, h omega is equal to omega m upon 2, which is equal to pi upon 2, right? Then only cos this particular part will be equal to 0. So 2k plus 1 is basically, we usually say that if we have a theta and if we add 2 pi, it will give us the same result, isn't it? Multiplied by k. So in this particular case, our theta is pi upon 2 plus 2 pi k will give me the same thing, right? Isn't it? So this is just the constant. So that is what is given over here. And then we need to solve for omega, and we end up with omega is equal to 2k plus 1 pi upon m. Is that okay with everyone? Did everyone get that? Hello? Okay. Okay. So I hope you guys can solve this, right? We just need to rewrite this into cos and sine part, and then we just need to evaluate the magnitude of that. That is, real value squared plus imaginary value squared, and the whole root of that will give me the magnitude. And using the trigonometric properties, we end up with 2 cos omega m upon 2, and then we just need to find at what value this tends into 0, because the magnitude of this particular term is equal to 0. And equating based on this, we know that cos of 90 or cos of pi upon 2 is going to give me 0. And that particular angle plus 2k, 2 pi plus k will be the same thing, right? So this is what is given here, 2 pi, right? Expanding this 2 pi k plus pi upon 2 is going to give me the same result, right? But our main focus is pi upon 2. And then what we do is we make pi, omega the subject of the formula, and we end up with omega is equal to this, right? K is an integer value. So whenever omega is equal to this particular value, we are going to get h omega is equal to 0, right? Question number 5.23, the frequency response of an ideal bandpass filter is given over here, right? This is given. We just need to determine the impulse response of it. So impulse response is basically h of n, right? Impulse response is basically h of n. So we are already given h omega, right? So the first thing that I would suggest, if we are given a piecewise function, is always plot this particular function, right? So if we plot this particular function, right? If we plot this particular function, we'll be getting something like this, right? We are going to get something like this. Right? We are going to get something like this, and then we can see based on these, right? Remember the table I showed you earlier, right? In week 5, 6, and 7, I showed you a particular table. If the function is continuous and discrete, what particular formula to use, right? In this particular case. So same thing is applied over here as well. So we know that this particular function is discrete, right? It is discrete, and we are not sure whether it's periodic or not periodic, right? And we know that we need to find a h of n. So if we look up that table, right? Let me just quickly look up for the table, just in case if you have forgotten, right? That would be Fourier. Is it Fourier series? Yeah, just Fourier series. I guess all of you remember this particular table, isn't it? Right? So in this particular case, we are just given the information about the periodicity between pi till negative pi. So we assume the system is periodic, and we, by drawing the particular h of n, h of omega, we know it's continuous, right? Right. So we know that the function is periodic, right? Since if we are given any information in pi and negative pi, we assume it's periodic, right? And we know that it's continuous. So our time domain function value can be evaluated by x of n is equal to 1 upon 2 pi from negative pi till pi, or from 0 till 2 pi x of e to the power of j omega multiplied by e to the power of j omega, right? So basically it can be given by this particular formula, and we need to identify h of n in this particular case, right? So let me go back to that particular screen where I was, right? So here we are. So we know it's we are not sure about the periodicity, but we assume that it's periodic and it's continuous. So basically, using that particular form, we can find the impulse response, that is the time domain response, right? So the time domain response is basically given by h of n is equal to 1 upon 2 pi. And since it is between this negative pi till pi, so we'll be using the limits as negative pi till pi. If it was given from 0 till 2 pi, we would have used the limit of 0 till 2 pi, right? And x of omega in the in the particular table, it is given x of e to the power of j omega. It is same thing. Basically, we are focusing on omega part, right? Omega is the varying part, not j. So we can rewrite that as x omega e to the power of j omega n d omega. So basically, we need to just feed in the function values and evaluate that. We need to integrate x of omega, right? So we know two methods, right? We can integrate from negative. We can integrate from negative. This particular part will be, sorry, this is negative pi upon 8, I guess. And this is negative 3 pi 8, right? So basically, we can integrate from negative 3 pi upon 8 till negative pi upon 8. plus integration of pi upon 8 till 3 pi upon 8, isn't it? That is one way. The other way we can look is, the other way we can look at this is basically we can integrate from here till here, assuming the magnitude is same, that is magnitude of 1, right? Since the magnitude is over here is 1. So we can integrate from this particular point up till this particular point, right? And then we can subtract this particular part, right? Isn't it? This middle part. So in this question, what they have done, they have used this particular method, right? So 1 upon 2 pi is just constant. We keep it outside. We integrate negative pi till pi of x omega multiplied by e to the power of j omega n. So we assume our x omega is 1 throughout between these particular limits, right? So if we integrate, this particular furthest point is negative 3 pi upon 8. We integrate from this particular point till this particular point, right? This is what we get. And then we subtract the middle part, this particular part. That is integration between negative pi upon 8 till pi upon 8. So we get this particular part, right? And then the rest of it is basically a trigonometry properties, right? Rest of it is your trigonometry properties. We can evaluate this, right? And we'll be ending it up with 1 upon pi upon n, right? Into sine 3 pi upon 8n minus sine pi upon pi n upon 8, right? And then using this particular property, that is cos u multiplied by sine n is going to give me this particular part, right? Using this particular property, we can further rewrite this particular term as this, right? I want you guys to try it out because I'm having some sort of limitations here when I'm teaching online, right? I cannot directly write it on the screen, right? So I want you guys to try it out, and then if you find it, if you still find it difficult, we can discuss it during our remedial session, right? And the final part of this particular question is that show that the impulse response can be expressed as the product of cos n pi upon 4 and the impulse response of the low pass filter. So we already have written the impulse response in terms of cos n pi upon 4, right? It is already written over here. So basically what they have done is rewritten the same thing as this particular form, right? So they have assumed 2 upon pi upon n sine of pi upon 8 multiplied by n as h1 of n, right? And basically taken this, right? And did a Fourier transform, and they have written this, right? This is useless, actually, unnecessary. So whatever we have, we can assume that this particular part is as h1 of n multiplied by cos pi upon n, cos of pi upon 4 multiplied by n, right? So basically the question had been already answered in the first part, right, over here. And whatever they have done is just, bullshitting around, right? So is there anyone with any sort of question? I know this is quite boring because there's not much to do. So is there anyone with any questions? Chat box. Hello guys, you're there? I think all of you have gone. Okay. So no question. Okay. Anyways, give me 2 minutes. I'll just quickly take the attendance, right? I'll take screenshot of the attendance. Okay, I had given a format for you guys to write, right? So Krishnil, Arshad, Lovikesh, please please rewrite your names or rewrite your usernames as, with your name and your ID, right? Edit your name and feed in your your student ID in the username, please. Just click on participants and edit your username, right? Just add your student ID to there so that I can update your attendance. Arshad and Luvikesh as well, please. Is Luvikesh even there? Luvikesh, please edit your username. All right, so I've taken your attendance, right? So can you just, okay, right. So tomorrow we'll be having our remedial class. So we'll be discussing your short test paper actually in the remedial class, right? So by the way, everyone is okay with the time, time for the remedial session? Or are you guys having some sort of clash? The time for remedial session is at 12 tomorrow. At 1 p.m. tomorrow. Is 1 p.m. okay with everyone? Or do you guys want it earlier or later? Okay, right. Then great. We'll keep it as 1 p.m. right? Tomorrow 1 p.m. we'll be discussing your short test paper, right? And then tomorrow in the following week, whatever questions you gather from this week's tutorial or from past year tutorials, past week's tutorials, we'll be discussing those questions in the next remedial session, right? Okay, that's it for the class. Just in case if you want to leave, you can leave, right? Otherwise, we are done with this week's tutorial, right?